Now we have reaction with oxygen. So what happens when anything reacts with oxygen, it forms oxide. So likewise they do. Alkali metal reacts with oxygen forming a metal oxide. They react and form a metal oxide, right. So but if we react alkali metal with excess of oxygen, we see different type of oxides among alkali metals. Like lithium, when react with excess oxygen, it forms lithium monoxide. It is lithium monoxide. Likewise sodium, when react with oxygen, it forms sodium peroxide. And when potassium react with oxygen, it forms potassium superoxides. So that means when the lithium is forming monoxide, that means it is getting crisscrossed with this ion, O2 negative. And when the sodium is reacting with it, it is getting crisscrossed with the peroxide ion, which is O2 2 negative. And when potassium react with excess oxygen, it forms potassium superoxide. That means it is getting crisscrossed with O2 negative. Right. Now you must be thinking that as they are member of same group, but still they are forming different types of oxide, as lithium is forming monoxide, sodium is peroxide, and potassium is superoxide. So what is the reason behind? The reason, the basic reason is that small cation can stabilize small anion. Small cation can stabilize small anion. Likewise, big cation can stabilize big anion. It is a fact actually. That means if we have a small positive ion, it can stabilize only a small negative ion. If we have a bigger positive ion, it can stabilize the bigger negative ion. That means the bond actually formed between them is sufficiently strong, and the lattice energy which is liberated when they both combine is maximum. So that means it provides stability to the compound, right. But what we observe in this case, that lithium, as we know that lithium is smallest of all. Lithium has the smallest size. So that means, I will just write here, it has the smallest size, and that means if we talk about its charge positive field, like it has, so it has a strong positive field. So what happened when it reacts with this oxide ion, it binds this oxide ion so strongly towards it because it has a strong positive field, because smaller the size, stronger is the field. So it could attract this negative ion with such a force that it won't permit this oxide ion to react with some other oxygen. So that means a smaller cation stabilizes the smaller anion so strongly, and the lattice energy release is you can say sufficient to impart stability to this compound. That is why it forms lithium monoxide. Now coming on to sodium, what happens compared to lithium, we know that Na positive has comparatively big size. So that means if we compare its positive field, so it has weak positive field as compared to this lithium. It has weak positive field. So that means it can attract the oxide ion, it can attract the oxide ion, but the attraction, the bond is not so strong. So that means in this case, when it gets bounded to sodium, it further reacts with one more oxygen. That means it reacts with a peroxide ion. If in total we take, it reacts with peroxide ion, and then only the stabilization occurs, then only the lattice energy is sufficient to stabilize this kind of compound. So that is why it forms sodium peroxide. So again the factor same, this bigger the size, the bigger anion it can stabilize. Likewise potassium is still much big as compared to lithium and sodium, and if we talk about its positive field, it will be having the very weak positive field, and it can stabilize one oxide ion, but it could not prevent the oxide ion in coming in contact with more oxide ion. That means that is the reason it combines with the peroxide ion, leading to the formation of potassium peroxide. So I think it's clear that the small cation can stabilize the small anion and bigger cation can stabilize the bigger anion. The reason being because small cation will be having a strong positive field, so it can attract a negative ion more strongly. But if we compare sodium and potassium, they are comparatively bigger in size and their positive field is less strong. So that means they can bind the negatively charged ion, but they cannot bind them so strongly, or do not prevent it in coming in contact with further oxygen and forming a peroxide or the superoxide ion. So this is the reaction with this thing. So now we can actually form lithium superoxides and sodium peroxides, potassium peroxide. Likewise we can do that. So if we superoxides. So if we look for the superoxide, we see it has one unpaired electron. in superoxide we see it has one unpaired electron, and due to which these superoxide compounds are paramagnetic. And we know that if a substance has unpaired electron, it has a color also. And that is why the alkali metal superoxides are colored, like lithium oxide and sodium oxide are yellow in color, potassium superoxide is orange, rubidium peroxide is brown, and cesium peroxide is orange, superoxide. I just used you can say superoxide and peroxide in place of superoxide. So keep in mind I am talking about the superoxides. So superoxides of alkali metals are colored because they have the superoxide ion has the unpaired electron. So lithium superoxide, sodium superoxide is yellow, potassium superoxide is orange, rubidium peroxide is brown, and cesium superoxide, and cesium superoxide is orange. But if we talk about the normal alkali metal oxides, they are actually diamagnetic, as they don't have any unpaired electron, and moreover they are colorless. So you have to keep in mind that whenever we react with excess of oxygen, we see variety of oxides, and the stability according to the size of the cation and anion just imply on this case, and you need to answer in that case. And if we talk about the magnetic character, so the superoxides are paramagnetic, but the normal oxides what we see, they are diamagnetic in nature. So this is what is the reaction with the oxygen. Now we will see the next more property, that is the reaction with hydrogen. So what we see that alkali metals actually react with hydrogen, forming the hydrides. For example, I have metal, I am going to react with hydrogen. What we will see, we will observe a hydride. This metal can be any member of the alkali group, lithium, sodium, potassium, rubidium, cesium, francium. But what we see, like as we move down the group, reactivity is actually decreasing with hydrogen. Like in case of oxygen, the reactivity was increasing, but here the reactivity towards hydrogen is decreasing. Same factor, because we know that small cation can stabilize the small anion, bigger cation can stabilize the bigger anion. So what we see in this case, that as we move down, lithium is smallest, it is comparable to the size of the hydrogen. But when we move down, sodium is bigger, potassium is much bigger, rubidium is much bigger, cesium is biggest of all. So but the hydrogen size remain the same. So that is why the bond form is not so strong, and that is the reason the reactivity of hydride actually decreased down the group. And if we see, like if we talk about that what kind of bonding they share, so we see that they are particularly ionic solids, they have ionic bond between them. But as we move down, the polarization character comes into view. And what is the polarization character? I think you remember we did in chemical bonding as well. Polarization is the distortion of electron cloud by cation of an anion, right, and as a result we have some amount of covalent character present in ionic bond. So the same thing happened in this case. As we move down, the size is increasing, therefore polarization is increasing, and that is the reason the ionic character is decreasing and the covalent character is increasing. Likewise, if you talk about reducing agents, so reducing character is obviously increasing down the group. The reason being because the bond is not so strong, so they can easily give their hydrogen to any other substance. And we know that the substance which can donate hydrogen is a reducing agent. So this is what we can say, that metal hydrides on moving down, particularly in alkali metal group, the reducing character is increasing. Now, and if we do electrolysis, you know that metal is positively charged ion, so obviously it has to go to cathode, and hydrogen is negatively charged ion here, so it particularly goes on the anode, and so that means we will get a hydrogen gas liberated at anode. Otherwise, the hydrogen is like here the hydrogen is having a valency of -1, otherwise hydrogen mostly serve as a valency of H positive and it is liberated at the cathode. But in this case, because it is serving a negative valency, so it will be liberated at anode and as H2 gas, right. So these metal hydrides are actually performing many important functions. Out of this, lithium hydride is serving an important function as it is used as a source of hydrogen, where in the military purpose for filling the meteorological balloons. So this is what like if somebody is going to ask you about the hydrogen ones, so you need to say that metals have a tendency, obviously have a tendency to react with hydrogen, forming the respective hydride, and the common thing or the important thing is that here the hydrogen is suffering as possessing a valency of negative, otherwise it always possesses the valency of H positive. So if we talk about the reactivity, it decreases down the group. Again, the size of the cation and anion is the factor. They are ionic solids, but as we move down, polarization is increasing because size is increasing. So therefore, the covalent character becomes more prominent there. And as far as reducing agent character is concerned, the lowest hydride act as a better reducing agent. As the bond is not so strong, it can liberate hydrogen. But as compared to the lithium, they are somehow stronger because the small cation can stabilize the small anion. You have to keep that factor in mind. And likewise on electrolysis, as it is serving as H negative, so obviously it will be liberated at anode as H2 gas. So this is how metal react with hydrogen. So this is particularly, you can say, a property of the S block, that they react with hydrogen forming their